Okay, so we're going to begin. Oh, by the way, there's some books that will be good for this course. The Hungerford book is a good one. Dummett and Foote is good because I don't think Dummett and Foote does this at the level of sophistication, the more mature kind of graduate presentation I'm going to give. But say what you will about Dummett and Foote, it's encyclopedic, right? So any kind of buzzword that you might want to look up is probably in there. I am also providing on my webpage and also on Canvas, I've got the course notes, which are probably chock full of typos and whatnot, but they'll give you an idea. I'm gonna follow the course notes. And we're starting about the middle. Basically, how many of you all had a college class last semester, right? Almost all of you. How many of you are planning to take a prelim and algebra? Right, so I think that actually part of what I'm gonna do in this class will help you not just in 85-10, because obviously this course is technically not on the syllabus, but it might help you with some of the 85-30 stuff. Because what we're gonna do is one of the applications is some stuff that will pertain to linear algebra. So let's start off. We're going to talk about modules. How many of you have ever heard of modules? Ever had any experience with them? Okay, so what is modules? So fast and loose, let me do this. So this has some connections to linear algebra. Modules can be considered a generalization of vector spaces that you all had to beat up on in linear algebra or two. Because actually what we're going to find out is well, here is sort of the universe of modules. Living inside here somewhere are vector spaces. And this is a module of the field. And field groups. So vector spaces, what do vector spaces have going for it? Well, if you think about a vector space in the old days, you know, when you first have a linear algebra, they list about 18 of these properties that a vector space has, right? But really a lot of that it's sort of at the beginning level, it's really saying a vector space is an abelian group, right? You can add vectors, there's a zero vector, there's negative vectors and so forth, right? And what else do you have with a vector space that makes it not just an abelian group? You have the scalar multiplication from the field. There's a way to hit these vectors with an element of the field and makes it still be a vector, right? Abelian groups are similar in the following sense. Abelian groups are modules over the integers, right? That is to say, you can multiply something in an abelian group by an integer. So suppose I take an element of the abelian group called G and I multiply it by 5, that just really means 5G. G plus G plus G added up 5 times, right? So modules are generalizations of vector spaces and abelian groups. Now, let me be honest with you. So let's start off talking about what a module ring is. Huge. Multiplication doesn't work. However, at the beginning, I'm going to relax that a little bit. We'll talk a little bit about left modules and right modules. But after a while, I'll kind of go just communicate. Yes.
What is actually the main problem for thing wants to generalize vector space within groups because variant is so nice, but works?
What's that now? So,
I mean, what was the main problem, but they want to go above like generalized vector space and appearance?
so the question is, why would you want to generalize this?
Yeah,
Well, the first reason, the reason I don't want to generalize it is because you can. And because it makes sense, right, to do so, right? But, there are many problems, even in something like number theory, where you don't quite have an abelian group. You've got something a little bit more, right? Because abelian groups obviously are very useful, right? They come up in a lot of things, right? Modules, have a little bit more structure to them, right? They're not structure theorems about it. And sometimes you have a vector space. What if you have a vector space or something that smells like a vector space? But you don't just have multiplication from, you don't just have multiplication from a field, it's maybe specialized. So for example, you might like look at 2x2 matrices of complex numbers, right? But actually, in important problems in, for example, number theory, algebraic geometry, form, might consider 2x2 matrices of the integers, right? You can add two 2x2 matrices of the integers to get 2x2 matrix. So this is a big group, right? However, I wouldn't expect that to have a vector space structure, right? Because if you multiply some 2x2 matrix, or just say the identity matrix, if you multiply it by 1/2, it's no longer got coefficients in it, right? For example. Does that kind of answer your question? So in this class, ring usually means commutative, and unless specifically specified, R has identity, whether it's commutative or not, right? I will assume it's got an identity unless I specifically tell you otherwise. So let's start off with the definition. A left R module and here R is a ring is specified, is an abelian group. Okay, so first and foremost, this goes into my generalizations of abelian groups thing. Equipped with a function R cross M and M. So that means that you've got sort of what we called in the days of vector space scalar multiplication. So we write notation we use for the order pair Rm in the domain, its image is Rm. Such that for all Rs and R and A, B, and M, we have a couple rules here. For one, R times the quantity A plus B is RA plus RB. We have R plus S. So in other words, this multiplication, if you will, in terms of scalars distributes nicely, and distribution works well when you sum over elements in R. And we also want some kind of associativity with multiplication. That is, So SA is now an element of M. And then you multiply by R, you should get the same thing. If you just take the big fat element RS and multiply by A. Unless otherwise specified. Unless I specify, we assume also that one R, an R, and assume that there's a one element ring. When I multiply by anything in the module, it leaves it alone. M is called, under the circumstance, a unitary. Or not. From the unit part of the range here. So, let me give you some terminology here. If if R is a division ring, is everybody familiar with this terminology? Just to make sure, a division ring it's sort of like the non-commutative analog of the field. A division ring means that every non-zero element of the ring is invertible, right? It's reciprocal, if you will, is in there, but it's not necessarily commutative. So a commutative division ring is a field. Then an R module. M is called a vector. Let me also call it an illustration, which I will leave to you as a simple, but call it illustrative example. So suppose you have that R model, you have R as an R and M is M, then R times the zero element of M, it's the zero element of M. So if you multiply any element of the ring times the zero element of the module, you have to get the zero element of the module. Verify that this is the case. And if you also get this if you multiply the zero element of the ring times any element of the module. Let A be a unit group. Any Billiard group that you could ever encounter, then A is a C module. Of course, it's the ordered integers. And let me show you the way this works. How does my module multiplication work here? Well, this is so if my integer is positive, then when I say n times a, what I really mean is just add a to itself n times. What are you supposed to happen if n is negative? Yeah, that's a good way to put it. Like that. And if n is zero, n, that calls a. So in a very natural way, any abelian group is a C module. Here's another example. This is a big fast vector space. If you've ever looked at this. Which is the set of all functions from the interval 0, 1 and the reals, such that the function is continuous. Back in the calculus days, for reasons that you probably puzzled about, then you probably were told at least that the sum of two continuous functions is continuous. And if you multiply a continuous function by a real number, it's still continuous. So that's what we got. We got an R module where here times R is a real number, so this is vector space. How many of you have seen this? Here's a bigger example. Ooh, that one's big. This is also a real vector space. By the way, and here's going to be some of the magic modules. Can you tell me what the structure of this is? It's a vector space. Both of these are isomorphic to some, say, collection. So both of these vector spaces look like this. Some number of copies of the reals, and the only thing that distinguishes these two as vector space is how big this is. In both cases, this one and this one, this index set has to be this one has to be bigger than that one. But that's actually a little bit of magic. This makes linear algebra almost trivial, right? Give me any vector space, any vector space in the world, right, over some field. I don't care what the field is. The vector space is some number of copies as a direct sum of that field. And to determine the vector space of isomorphism, all you need to know is the size of the index set, right? And that's something we will get to later. Here's another good large family of kind of examples. 3. R is a ring, and I is a left ideal. Then right? What do you know about ideals? You had two elements in the ideal still in there. Okay, so you get the abelian group kind of thing going on there. And what does it mean to be a left ideal? When you multiply anything on the left, take any element in the ideal, multiply it on the left by something in the R, it's back in the ideal, and it does our little rules, right? So any left ideal is a left R module. It's probably worth noting here that, this is usually not an exhaustive, collection of left ideals. So 3B, note, C mod 2, and Q are, ideals, or are C modules, but not. So here's another sort of generalization. If you specify the ring that your module's over, you can consider modules to be a generalization of ideals. Okay. One more kind of good standard from your toolkit. If you have R inside of T are rings, then I'm thinking of this in terms of commutativity, but it doesn't matter. You can do what thing you want. Because notice T is of course an abelian group, right? And when you multiply anything in T on the left, if you like by R, it's still in T. So T is an R module. This is another kind of interesting example. Let me give you something a little bit more exotic. And we're actually going to come back to this example later. This one actually has some interesting applications in linear algebra and decomposition of matrices into canonical forms. How many of you have had 85, 30? Okay, a couple of you. So did you all do Jordan canonical forms, that sort of thing? How did you do it? Did you do like generalized eigenvalue or eigenvectors? Well, I'm gonna do it a different way. So let's here's my more exotic example. Let F be a field. And B a vector space. Over. So any field in vector space you want, and let's say T from B to B is a fixed linear transformation. So this sounds like I'm teaching a linear algebra, right? I've got some fixed field, some vector space, and some fixed linear transformation. I am going to make V an Fx module. Okay. V is an F module. No surprises, right? Because V is a vector space, right? And that's, but I'm going to do this. I'm going to make this a module of polynomial. How would I do that? Well, here's your scalar. This is some polynomial, right? And I multiply it by vector V. Here, f of x is in fx, some polynomial is in V. Now I need this to barf out another element of V. How can I do this? Any ideas? There you go. We're going to use this as since this is fixed, I'm going to use this as a tool. F of t is still a linear transformation, right? Because, what do I mean by F of t? I mean sort of plug the linear transformation in. When I plug t in for x, it's just t. When I plug t in for x squared, it's x squared. And of course, when I plug it in for one, it's the now this is a linear transformation. And just operate on v, so so this times this, that gives me an output in v. And it's easy to check that this is an R module, right? Or I'm sorry, an FX module. And we'll, like I said, we're gonna apply that later. Okay. Oh, wait, and I am gonna do one more. We're gonna talk about these refreshes. Well. This is an important question too. Suppose I have a collection of R modules, just a whole bunch of these things, MI, indexed by some possibly huge set. We can make M for some R modules. Remember, these are constructions. Remember, first and foremost, these MIs, these R modules, they are first and foremost abelian groups. That's what they have to be. And so those constructions, the direct product and the direct sum, still an abelian group, right? Does anybody remember the distinction?
Was only a finite number of copies are not the identity.
Right. So you might consider this, since this might not even be countable, I'll call this a net. This is like a generalized sequence of elements in here. You've got complete freedom here. And this one, in your generalized net, all the entries are zero, except for finitely many, and most finitely many are not zero, right? And I think there's a natural way to do this. So, for the first one, I have R. Well, actually, I can do this for both of them. When I multiply something in R times one of these things, if it's in the direct product, I've got complete freedom. If this is in the direct sum, most of these have to be zero, right? All except finite many. Where do you suppose my multiplication rule is? Got to have a new sequence. And remember, folks, this is math, and so it's not easy. You shouldn't do it. What's the natural thing? Right. And these things are all in each respective. So that's an important construction as well. Okay. Now, this is what modules are, and these are some examples of modules. I hope are helpful in putting together your first kind of tool by these things. As is the case in algebra, after I tell you what the structure is, what's the next thing I'm going to do? Let's answer this kind of questions. What am I thinking, right? What's the next thing that almost always you do in algebra? You start talking about morphisms, right? The maps between these things, right? And the good news is really the first hump when you first do groups, you do like, the first isomorphism there and second. After that, everything's just a copy, right? All these theorems are kind of simple. So let's first define what it means to be an R module morphism. Definition. 613. The modules. The function F made B is a left R module homomorphism if there's gonna start, there's gonna be two rules that I don't think are gonna surprise you. F of x plus y is f of x, f of y for all x, y, and a. No shocker there, because what this basically says is this is an abelian group homomorphism. That's all this says. Because first and foremost, A and B are abelian groups, and this just means it's respecting the abelian group structure. To be an R module homomorphism, it has to respect scalar multiplication. So this is very similar. This is linear transformations, if you will, for modules. So, little terminology. Yeah. A, B, vector spaces. That is, if R is division. Then F is called a linear transformation. So if this looks familiar, like something you've seen in linear algebra before, it's because that's exactly what it should look like. Okay. And you probably saw something like this, probably in a good linear algebra class. Here, actually. B from end to end is an R module homomorphism if and only if B of x plus R y is equal to B of x plus R B of y. For all x, y, and m, or one direction is very clear. If it's an R module homomorphism, then you can break this up into phi of x and phi of ry, and then in the second step, R. I'll leave it as an exercise to show the other direction. It's not difficult, but might be good practice. Of course, let me also point out in this definition before I give you another example here. If the ring, if R is Z, then A and B are just abelian groups. And this is exactly this is exactly, what you need from a building group home focus, right? In fact, all you really need is this, and if the ring R is Z, then this is superfluous, because R is an integer, and this would follow from this, in the case that R is. Okay, any questions? Let me give you, an example here, kind of a non-example, sort of. Let's look at, yeah. Disease. Where n can be an integer. So basically, the function here, Fn, what it does is it just multiplies any input by n. This is a Z module homomorphism. See, because Fn of K1 plus K2 is n times K1 plus K2, which you can break up as n K1 plus K2, and there you go. So it's a homomorphism of the groups, and that's all you need. But is usually not a ring. Anybody discern when it is? I'm gonna do this. It's clearly a ring homomorphism if n equals one, right? Because it's just the identity of that. Do I agree with that? Now I'm going to take the notion of ring homomorphism that you have to take 1 to 1, right? Some people define this. Now, you said that it could be 0, it depends on, so we could get in a big categorical argument of this. I can't really quibble too much with that, but if you demand that 1 has to go to 1, once I make that demand, it's clear that the only way for 1 to go to 1 is for n to be 1. Right? So these are good examples, modular homomorphisms that aren't ring homomorphisms. So there's all kinds of adjectives also. Once we have modular homomorphisms, we can stick all kinds of adjectives on it, right? Like they can be a monomorphism or an epimorphism, 1 to 1 or onto, but they can be an R module isomorphism, so 1 to 1 and onto. So anything like that follows old terminology that you have, but if there's any questions, just bring it up. Here is another important so I bring this proposition up. This will also serve to define this nice class of modules. Let M R modules. And you'll see in the proposition column where we could also take these to be leftover modules. How many of you have ever seen this sentence? Home means homomorphisms. Sub R means the R module homomorphism. So this is the collection of F and then the M, such that F is an R module. Homomorph. Uh, I'm doing group. I guess let me be precise about what I mean by this. So if I'm gonna tell you an abelian group, I've got to tell you how to add functions. So, if F and G are M, home are M, then what do I mean by F plus G? What is the function F plus G? Well, F plus G of M is defined to be, F of M. So this is the way you add functions in calculus, it's just the point-wise, addition of functions. This makes home RMN into an abelian group. And of course, abelian groups, right? That's already got my spidey sense tingling, right? Maybe we'll go further with this. But let me add the statement here. Additionally, R is commutative. Then home R, N is an R model. And of course, the way we find this is R times F of M. R. You might ask yourself, what could go wrong if it's not commutable? Right, so see if you can figure that out. And remember, these have to be R modular morphisms. All right, so let us. I'm leaving some of the stuff at the beginning, exercises, how it's completely spellbinding to you, just let me know, I'll be happy to throw in a proof here. We'll start proving things pretty soon. Definition. 6.8. Let M be a left R module and N a subgroup of M. So what I'm seeking to do here is find what needs to be a submodule. Now, my goodness, if it's gonna be a submodule, it better first and foremost be a subgroup, right? That's gotta be at the basis of it. And what do you suppose is the natural thing to sort of, so if I want to try to define a submodule, it better be a subgroup. And what do you suppose I need? Other condition on N I need logically to make this a submodule. You know, yeah,
all under the same, action.
Right. It's gotta suck, right? Right, when I multiply anything in R by anything in N, it's still an E. And this gets me what I wanted, right? Basically, just as before, sort of the fact that this is a submodule, the properties follow from two things. Number one, it's a subgroup of M, and number two, when I multiply something in R times something in N, it's still an E, right? And that's what we're gonna need for a submodule. So this is our definition. So we follow the proposition. Let R be a ring and M a unitary level module. I always assume this, but it's gonna come up, I think, with proof. R module. Then M is a left or submodule. Uh, if and only if X plus RY. So for all X, Y, and M and R and R. And let me just say, actually, for one direction, I don't mean N is not empty, but so we'll assume that N is a non-empty set. Okay, that's enough for now. We'll look at why this is true next time, but does anybody have any questions for that? All right, well, y'all have a good one, and we will see you by Friday.